那个对我们7点钟了，我们开始了，要不
OK，
等会儿再聊。
OK，
那个同学们，那个同学退流了吗？Hello everyone. Welcome to today's online webinar of AsiaGraphics. It's our great honor to invite Professor Jin Mingzhen from Nanyang Technology University and Professor Yi Liao from Zhejiang University. In the first part, Professor Jin Mingzhen will give the talk followed by question and answer, and then Professor Yi Liao will give the second talk. At the beginning, let's go to the first part, and let me introduce Professor Zheng. He is a professor in the School of Computer Science and Engineering at Nanyang Technology University. He received his bachelor degree and PhD from Zhejiang University. His research areas include computer graphics, geometry modeling, visualization, and AI for design and 3D printing. One of his famous work is to design the T-spline technology that has been widely used in CAD and CAE industry. Today, he will talk about 3D shape passing from point cloud. Okay, let's welcome.
Okay, thank you, Jiyo, for the introduction. So good evening, everyone. So I'm thankful to Prof. Ligang Liu for inviting me. So I'm very happy to have this opportunity to share my research via the AG webinar, right? So the title of my talk is 3D shape passing from point clouds. So the title actually indicates the talk is about 3D point cloud, especially shape represented by 3D point clouds and shape representations, and also shape passing or understanding. So to me, these topics are quite interesting and exciting. So they actually contain some fundamental research issues, research problems, but meanwhile, they have some practical value. So in this talk, I will share some of my research in these topics. And particularly, so I will present 2 recent work accepted by ICCV last year and ECCV this year. So this work was done by my PhD student, Ren Daxuan, and they are also the outcome of this collaboration with Professor Cai Jianfei at Monash University. Excuse me. So when we talk about the shape representations, it's related to the digital 3D models, right? So as a type of the media data, as digital 3D models actually have wide applications. And in early times, so those models are used in like a CAD/CAM industry. And later on, 3D models appeared in like animations, movies, and games, right? And scientific, research, visualizations, and also engineering simulations. And nowadays, 3D models are also very important, for example, for metaverse applications, and also digital twins. Okay, so the digital model of the real-world objects are of great interest. Actually, they are something reality computing focuses on. So look at this picture on the left side. So it's a side of the Haw Villa. Haw Villa is a park in Singapore exhibiting some Chinese and Asian culture. So on the request by the Travel and Tourism Board of Singapore, we digitize this site. So we create a lot of point clouds, and then we process point clouds to create a virtual model. So here we can see, okay, nowadays they're relatively easy to obtain or generate point clouds. And the point clouds are unstructured. So they do not provide those semantic or high-level information explicitly. So, however, in many applications, high-level representations and high-level understandings are required because they help us to understand the shape, understand the thing, and also benefits many high-level processes and analysis. So there's a lot of research done in these directions and try to create the high-level representation from low-level representation, such as a point cloud. So the first step, like I say, okay, 3D reconstructions, right? So 3D reconstruction converts the point cloud into the mesh. Right? So compared to point cloud, the mesh are more compact and more structured. At least the mesh and conveying information of how vertices are connected with each other. Right? But the mesh themselves are still low-level representations. They do not explicitly provide high-level information or semantic information either. So this slide actually shows the work done by Professor Ju Yongzhang. So the next step, say, go to the shape decomposition. And actually, this is also the Ju Yong's work, actually part of his PhD thesis. So here, okay, shape decomposition partition the objects into meaningful parts. Actually, this is hard. So we like to each part, okay, match the human shape perception. So this conveys some high-level information or high-level representation. This helps us understand shape and benefit the high-level editing, for example, example-based editing. And in industry, actually, there are some special requirements for high-level representations. For example, in building and construction industry. So BIM is a model containing some high-level informations. So in a recent project with Sabla Junon, so we are required to create a BIM from scans. Actually, this is a quite challenging problem, especially to construct a BIM model from scan automatically. Right? Sabla Junon is a local company in Singapore. So in another project, I undertook, that's the Virtual Singapore project. So we are required to create a model in CTGM format. And the CTGM format is a file widely used in GIS applications. It contains several levels of details, so representing the different level of the informations. So we developed some tools or semi-automatic tools which can convert like the point cloud or mesh into like a CTGML, like a LOD2 or LOD3. Okay, those are some research we did in the past. Right? So my current interest falls in the following problem. So now if we are giving objects represented by point cloud, so how can we convert that into high-level representations? So this actually is quite a fundamental problem, right? So, so the definition of the high-level representation is quite subjective and depends on the application, depends on the scenario. Right? So we propose some criteria for this. For example, okay, high-level representation should be compact, right? Not like a point cloud, there's a lot of points. So we should have a more compact representation for the shape. And the second is the shape should be intuitive and we can understand each component. And the representation should be easy for further editing. And moreover, we like high-level representation. It's easy for learning process. So those are some basic requirements we want high-level representation to have. So like checking some literature of the geometric modeling, and we find the CSG tree might be a good high-level representation for this purpose. So CSG actually stands for solid constructive solid geometry. It's a popular and also fundamental representation for geometric model, especially for solid model. Right? So it's compact and editable and also interpretable. Right? So in CSG, the object is represented by some simple shape, such as like here, like a box, sphere, a cylinder in this slide. Right? So you can see those simple shapes can be defined by only a few parameters. So it's easy to edit. Right? But on the other hand, you can find that this CSG tree, right, could have different structure. The structure is quite dynamic, depending on the scenario, depending on the object. So this might make difficult for learning process. So let's check the fundamental elements of CSG. Right? It has two components. The first one is the primitives. So here I'm usually like a box, cylinder, sphere, and cones are the primitives for CSG, and these serve as a building blocks. And the second element of CSG is Boolean operations, including intersection, union, and difference. So those primitive objects are recursively combined by Boolean operations to form more and more complicated shapes. Right? So eventually find a single object. So that's a CSG representations. So as I mentioned, the CSG tree might not suitable for learning, or it's at least difficult for learning. So to get rid of this dynamic nature of CSG trees, so our basic idea is to flatten the CSG tree. I flatten the CSG tree. So we try to group the same Boolean operation together, for example, all the intersections together. So in this way, and eventually we come up with a fixed 3-layer structure. So we call the CSG stem. So CSG stem has 3 layers. The first layer is called the complement layer. Right? So it's applied to or correspond to the primitive object. And the information tell, okay, whether this primitive remains there or should we use the complement of this primitive. Right? The second layer is called the intersection layer. Right? So intersection layer tells, okay, which node in the complement layer should be included in the intersection process. And in the third layer is a union layer. So it tells, okay, which nodes in the intersection layer, the second layer, should be included in the union process. So eventually used to define the final object. Right? So in that case, you can say each layer has a very clear rule, and also the structure is fixed. So we call it like learning friendly. Okay, here's an example. We have a mechanical part. Right? This mechanical part can be represented by a CSG tree or CSG stem. Right? And both representation involve 8 primitive objects, like 2 boxes and 5 cylinders and 1 cones. Right? So now we like to propose a question. So okay, can both representations of both structure equivalent? So that is okay. Can both representations be converted to each other? Right. So this is actually important. So the answer is yes, and this can be proved mathematically. So the conversion from like CSG stem to CSG tree is obvious. Right. So we just, if you understand the property of those union and difference, those Boolean operations. And the backwards conversion from CSG tree to CSG stem can be proved by induction. So let's look at the base case of where there are only 2 primitive objects like P1 and P2. Right? So for example, when we do the intersection, P1 intersection P2, and this is from CSG trees. But we can formally represent this guy as a CSG stem form. Right? So we introduce an empty set. We use a C for this whole space. Right? So then you can say, okay, so the primitive level, you have P1, P2, and also empty set and the whole space. Then we do complement level, we don't do anything. Then do the intersection, second level, and third level to the union. Right? So similar analysis can apply to union and the difference. So then, okay, by induction, you can prove, yes, I mean, any CSG tree can be converted into CSG stem. So that means both representations are equivalent. So that means CSG stem can represent any CSG tree. Okay, now to realize the concept of CSG stem, right, we need to design some appropriate data structure. So we have seen that the CSG has 2 parts, primitives and Boolean operations. Right? So for primitives, we use some parameter called intrinsic parameters, extrinsic parameters to represent the primitive shapes. For example, a box, right? Intrinsic parameters are 3 edge lengths in its standard position. So in standard position, that means the center of the box at the origin, the edges are aligned with those XYZ axes. Right? Similarly for other primitives, extrinsic parameters include the translation and rotation transformations, and they make the standard primitive objects in the required location and in required orientation to form the final shape. For, like, say, connections or Boolean operations, so we introduce 3 binary matrices to encode these connection layers. In particular, for the first layer, for complementary layers, so we use a matrix WC. Like, WC has a size of 1 by k, and k is the number of the primitive objects. Okay, so this binary matrix, the entry has a value either 0 or 1. Right? So 0 means, okay, we don't perform complementary, so the primitive object remains there. But if the entry value is 1, that means, okay, we use the complementary to the primitive object. Okay, the second layer, so we use another matrix, WI. I stand for intersection. Right? So WI is for the intersection layer, and the matrix has a size dimension of k by c. Right? So the rows correspond to the number of the node in the first layer, or the primitive object, and the columns correspond to the number we set up for this intersection layers. Right? So that is okay for each element in this matrix. If the value is 1, then we say, okay, so the object, the node in the first layer should be included in the intersection process. But if say, okay, the value is 0, entry value is 0, that means the corresponding entry is not included. And the third matrix is WU. WU is for union, right? So the size is C by 1, and C corresponds to each node in the second layer, intersection layer. Right? Similarly, the value 1 represents the corresponding node should be included in the union operation, and 0 representing, okay, that node is not included. So in this way, so eventually, the sage star will store like the primitive object in terms of the intrinsic, extrinsic parameter value, and 3 binary matrices. All right, so then we also need some ways to represent the object and each node in the sage star structure mathematically. So mathematical representation sometimes allow us to well formulate the various application problems and or do optimizations. Right? Considering that Boolean operations are involved in sage star, so it's convenient to introduce the occupancy function for the object representation. So actually, occupancy function is widely used recently in neural representation of the shapes. So here, for example, for particular object O, so we use O of P as the occupancy functions. So then for a point belonging to the object, so O of P equal 1. So otherwise, O of P equals 0. So this is easy to understand. Right? So in this way, so we can say for the empty set, so its occupancy function is identically 0. For the whole space, its occupancy function is identically 1. Okay, then for each node in the first layer, complementary layers, right? So we will say, okay, we use Fi to denote the occupancy function for that node. I stand for the ith entry. So in this matrix, we store value 1 or 0. 0 means the corresponding node don't perform complement. right? So that means the primitive object remains there. So then you look at these expressions. So if the entry value is 0, that means second term vanish. The first term gives you OI or OP. That's the occupancy function for this primitive object. But in case, okay, a particular entry has a value 1, so then the first term vanish and second term give you 1 minus OI. So that's the occupancy function for the complement to the primitive object. Similar for the second layer or the intersection layer, for each node, we use the SI to represent the occupancy functions, right? So S stands for the second layer. So I for the ith entry. So in the matrix, okay, so the I column are used to represent this node. Right? So for each entry in the ith column, so we tell, okay, the corresponding entries in the first layer will be included or not. For example, okay, if a particular value is 0, so then Wi will vanish, the second term will vanish, and the first term gives you a value 1. That's maximum value. And the maximum value 1 will be ignored later on due to the use of minimum. But if the entry value is 1, so the first term vanishes, second term gives you F, J, or P. That's the occupancy function for the node in the first layer. So that's something we want. Right? And also know that say in Boolean operation, the intersection can be achieved by the minimum function for the occupancy function. So that's reason here we use a minimum here. So for the third layer, there's only a single node called root node, right? So we use a T, P as the occupancy function for the root node. So T stands for the third layer, right? And actually T actually represents the occupancy function for the final object, overall object. So the matrix for the third layer actually is a column vector or matrix of C by 1. Right? So you can say entry has a value 1 or 0. So 1 represents the corresponding node in second layer will be included in the union process. So the occupancy function of the corresponding node in the second layer will be included. But if the value is 0, so then this expression will give you 0. So 0 will be ignored due to the use of maximum function, because union function can be achieved by maximum function. So that's the reason here we use the maximum function. Okay, so those are mathematical functions which can be used to represent each object and also each node in the CSG stem structure. Okay, so with all this ready, so we can formulate our 3D shape parsing problem, right? So the CSG stem, you can see, is quite flexible and fundamental representations. So now our problem is like this way. So the input is a shape given by point cloud. And we want to reconstruct the CSG stem representations. So that is, so we output a set of primitive shapes. So by its parameters value. And the 3 connection matrices tell how those shapes are combined. Right? So this by nature actually is an inverse problem, right? Generally quite challenging. So the first approach, okay, we propose to use a binary programming. So that involves 3 steps, right? The first step, actually, we use some existing method, like the occupancy network proposed in CVPR 2019. So this allows us to generate a target shape occupancy function. So for point cloud, we create the target shape occupancy function, and this serves as a target function. Then we run ransack to predict the primitives. So how many primitive objects we need, and what are those primitive objects? So then you can say, okay, to build the CSG stem, what do we need? Just to find the connection layers. So the connection matrices can be found by find the solution of this minimization problem, right? So here in this minimization problem, the variables are 3 binary matrices, WC, WI, and WU. Right? All the entries are just by number, either 0 or 1. So that's the reason we call this a binary programming. Okay. So we like this predict the occupancy function for the final shape, match the target occupancy function as much as possible. So this is a minimization problem. Right? So, but in general, you can say, okay, this predict the occupancy function actually is a composite function. It's quite complicated. Right? So we use this global optimization to solve this problem. Right? So this simplifies our job. So it works pretty well in general, especially for simple shapes with just a small number of those primitive objects. So especially if the number of the primitive objects is less than, say, like 10, it works quite well, right? As shown in these two examples, there are only 5 primitive objects. But if for objects is very complicated, its shape is very complicated, or there's a lot of primitive objects, then this approach will take a long time and might diverge, might not converge. Right? So that's the reason, okay, we turn to seeking another approach using like machine learning to find a solution. So for that purpose, we propose SageStarNet. Right? So here is a basic architecture of this net, very relatively quite simple network architecture. So we use some traditional like net backbone to encode the point cloud, input the point cloud into some latency feature vector. So then we design MLPs to decode the latent vector into primitive head and connecting head. So primitive head just tell, okay, how many primitives and those parameters, intrinsic parameter value and also extrinsic parameter value. And the connection head actually to recover those 3 connection matrices, right? So for those primitive objects, based on those parameters, actually we like to compute the occupancy function. So that eventually we can compare with the target occupancy function as a loss, right? To learn this process. This is a unsupervised learning. And to make the process more stable, there's some tricks we can play here, right? So especially to define the occupancy functions. So usually it's a kind of binary, right? So it's not, differentiable. So we take some, follow some idea of existing work. We compute a signed distance function, right? So or construct a signed distance field and then use a sigmoid function to convert a signed distance field into occupancy function. So in this way, can make the algorithm more reliable. And similarly, okay, there's some other trick you can play, like the loss function, you can add some terms, and also the maximum minimum function can be replaced by the relaxed version using, for example, the softmax, right? And also for the connection matrices, the entries are just binary, but we can relax this to, like, say, to find some soft value between 0 and 1. Also use some other way to do that. And eventually, then you just do a threshold to that, and this can make this learning process more reliable. Okay, here's some examples. Okay, some experiments. We performed on this data set called the ShapeNet. So the ShapeNet was produced by research group at Princeton University and Stanford University. The data set contains a few models which contain quite a lot rich information. So we compare our method with the UCSGNet, right? So you can see visual effects, and here also visualize our result. So we also compare with the other state arts in this type, like the VP stand for method assembling with the volume primitives, and SQ stand for the method using super cortex, right? And UCSG, just as I said, is an unsupervised CSGNet, right? So eventually, we will also do this comparison quantitatively. So, and here we measure the error using transfer distance. And you can find the CSG sum actually gives a minimum error in average. So, and more evaluation is presented in our paper. So we evaluate using other metric. But overall, we can say, okay, the performance of CSG sum actually is quite good, or it's on par on the state art, and or even better than the performance of state art. And also we can say, okay, so eventually the result is quite compact, involve only a few primitive objects. But here I just show the second layer, so not so many elements we need in the intersection layer. But in the primitive layer, we need more primitives, but still not so many. So eventually the representation is quite compact. And then moreover, okay, since eventually you output the object in can say CSG-like representation, it's compatible to existing CAD software. For example, you can use like Fusion 360, the Autodesk product, or you can use the open SCAD software to do the further editing. This is just one example, right? So this editing is high level, right? So a few parameters you can adjust, and compared to point cloud, this is much easy to understand and more intuitive and flexible. So the implementation of this CSG stem can be found in my students' GitHub. Nice. Okay, so those are some interesting structure, especially so personally, I like this CSG stem structure. It's quite fundamental and simple. So then, okay, what's next? So we like to explore something beyond CSG, right? So we can say, just as I said, the CSG stem actually give a very simple description for Boolean operations. So that means for some application require Boolean operations, not necessarily CSG. So CSG stem might be also used for that application. But meanwhile, okay, in traditional CSG, the primitive objects are quite simple, just as I listed earlier, like the sphere, the box, the cylinder. But in real situation, we can actually extend the generalize of the primitives to more general situation, right? So this actually gives us some hints to do the further exploration, especially to check this actual modeling process. For example, okay, in many CAD applications, and people actually do the modeling using a process called a sketch, and then do the extrusion. This is quite an intuitive process, widely used, especially in industry, CAD industry, right? So here you do the sketch, draw some circles, straight lines, or freeform curve like B-splines or Beziers, then do the extrusions and create very nice shapes, right? So we like to, okay, to reverse engineer this kind of things. And this tells us compact representation, still high level representation, but meanwhile, we also know the modeling process. So our basic idea here is, okay, given point cloud, so we try to figure out the sketch, the 2D sketch on the sketching plane, then do the extrusion, and that form one part of this reconstruction shape. Right? So that's the basic idea. So eventually, okay, we can reuse the framework we use in CSG stem. So that involves 4 components. The first one, we still use the encode-decode architecture to generally require the parameters for this extrusion parts, right? But this can be done using like a dynamic graphics CN network, and to do the encoding. And for decoder, we still use MLP, right? Then we need some representation for sketch. How can we represent these extrusion shapes, right? So that's something we have to explore, right? But meanwhile, okay, for the new primitive object, we should have some way to compute the occupancy. So that's something we also need to develop. So after that, you already have quite a few extrusion shapes. We have to assemble them. So, but this can be done by CSG stem. So then you can say, okay, in this framework, so the first, last, we already know. So then we pay attention to the middle 2 components. Right? So then you say, okay, what about the sketch on the plane? Right? So here you have to trade off the complexity and the reliability. Right? So we'll find, okay, sketch should be a closed curve, right? And should have no self-intersection, because otherwise it makes the situation very complicated. But meanwhile, okay, in real application, especially CAD industry, so the shape is smooth, or at least the piecewise smooth, right? And should have the capability of modeling like freeform curves, circle, and polygon. So in this sense, okay, so we propose some ways, some strategy. For example, we use a polar form to achieve this close, to realize this close requirement and no self-intersection. And use, okay, rational Bezier to represent the sketch. Right? So in particular, say, eventually a closed curve is formed by several segments, for example, n segments. And each segment is a special rational Bezier curve. In particular, we use a cubic Bezier curve defined by 4 control points and 4 weights. But the special, we just fix the first last weight to be 1. So eventually we have only 2 inner weights. Right? So this is a special rational Bezier curve. So in that case, we reduce the number of the parameters, because if you have too many parameters, it's difficult to learn. Right? Okay, then we just say, okay, distribute each segment evenly along the origin to form a closed shape. Right? So that case, for each segment, we have a central angle of 2 pi over capital N. Right? So then for each Bezier curve, the control points we represent by polar coordinates rather than Cartesian coordinates. So we have rho as the radial coordinates and alpha I as the polar angle. Right? So then, furthermore, we define the polar angle in some special way for one segment. For example, okay, you have 4 control points. So if the first point has a polar angle alpha 0, then the second control point, its polar angle is alpha 0 plus theta. Similarly, okay, so the last point, the polar angle is fixed because we already know the central angle for this segment. Then the P2, the polar angle is the alpha 3 minus theta. Then what's theta? Theta is a specially designed angle. It's computed like this way. Then you may ask, okay, how you come up with this complicated angle? Actually, we do some reverse engineering. So this angle is specially designed to achieve required properties. So I will show that in this way, we can reduce the number of the parameters. Or now you can say for those 4 control points, all those polar angles are fixed. So we only have the radial coordinates, right? So there are only 4 radial coordinates plus 2 inner weights, 6 scalar number. So then, okay, such sketch curve has the following properties, which actually sets our requirement. For example, they form a star shape, right? So since the angles are distributed in a special way, so this closed curve form a star shape. Each point can be viewed by the center. And also 2 adjacent curves can meet with the C1 condition if those control points are specially designed. A weight and a control point satisfy those conditions. Geometrically, that means those 3 points are collinear. Right? But of course, if the condition is not satisfied, then those 2 curve segments meet with only C0 continuity. This actually reduces the number of the freedom. So there's some constraint on those parameters. Right? And you can say for each segment, if all the control points are collinear, like on same line, then we can say this curve is a line segment. And this is due to the well-known convex hull property of the rational Bezier curve. Right? In particular, since we're interested in the circle, so you can say we can prove that. Actually, you can find the proof in our appendix of the paper. So if you set the radial coordinates properly, and also set the weights properly in this way that involve the angle theta, then we can prove the rational Bezier curve is a circular, arc. So in that case, we can represent the circle exactly. Right? So those are some representation for our sketch curves. Right? So then, okay, so with the curve, just as I said, to compute the occupancy function, we have to compute some signed distance function, So usually for rational Bayesian curve, it's difficult to do that. And we propose a general approach, numerical approach. We sample all those points on the curve, right? Give a numerical way, and then give a numerical to compute the signed distance function. And right side to show this signed distance field for all the points. You can see this field actually quite smooth, right? So now the issue is, okay, for this extrusion object in 3D space, how can we find the distance function? So for example, for point P here, so I'd like to find the signed distance function with respect to this extrusion part. Okay, that's complicated. However, we use extrinsic parameter rotation matrix and the translation vector T. We can transform P back to the standard coordinate system P prime. Then, okay, compute the relative signed distance function with respect to this standard extrusion. So the extrusion defined by the sketch curve on the XY plane and also extrusion height h. So we find and formulate the formula in 3 functions. Eventually, we have explicit representations, like using minimum maximum functions. But eventually, minimum maximum function can be replaced by relaxed version. Right? So this can simplify our learning process. So eventually, we have similar network architecture. So input a point cloud, then we do the encoding into the latent vector. Then we do decode and decode into the shape head and also decode into the connection head. So then during learning process, and we can learn the extrusion part, the extrusion parameters, intrinsic parameters, those are rational Bayesian definition, and also extrinsic parameters like rotation and translations. So those are some results, okay, by our method. So looks just as you can see, actually the performance is pretty good and even better than previous CSG stuff in terms of the chamfer distance. Right? And also we do some evaluation of this 2D sketch and give the very good approximation for the signed distance field if the sampling point is large enough. Usually, okay, for each curve, we choose 100 or 200 sample points. That will be enough. If we increase, then you will reduce the error, but not so significantly. But that will increase the computation time. But if the sampling number is very small, then the accuracy will be sacrificed. Okay, so then you can see some results, and the results are in high level because in Bayesian representation. So it provides a control points a way to do the further editing. So we can input the output of network into some CD system. Then we have Bayesian control polygon do the further editing. So this kind of editing is high level. Right? So this is just illustration of our process. So you can also find the code in my students' GitHub site. But so then, okay, so the network can figure out those sketches for the particular object. Then also can estimate the extrinsic parameters, the rotation and translation, and also the extrusion height. So now we assemble all these extrusion parts to form the final shape. Right? So this is according to those connection matrices. Okay, due to time, I just skip over there, just come to the summary. So in this talk, so I show some work about 3D shape parsing. Right? It's a quite interesting task and quite useful in practice and fundamental problem because it covers some high-level components and representations for 3D shape, especially for 3D shape initially represented by low-level data like a point cloud. So this talk also presents a 3D stamp structure, very simple structure, which is very suitable for describing Boolean operations. And also present extrude net, which can reverse engineer underlying constitute and modern components, and also the extrusion process for 3D shapes. So I would say, okay, those work are not necessarily best, right? Or I mean, so just some initial attempt in these topics. So there's still a lot of room for further improvement and still a lot of space for further explorations, right? So that means more research is needed. So I look forward to more research and new research outcomes in near future. Right.
Okay.
Okay, so then I will end. Right.
Okay. So many thanks for Professor Zhen's wonderful talk and very good work. So in the next, we go to the question and answer session. So there are several questions, and okay, the first question is that in the first work, are they basic geometry elements fixed or not? If they are fixed, is it possible to learn the basic geometry elements in the CSG stamp framework?
So usually, like say, okay, in I mean traditional CSG method, right? CSG representations. So the primitive objects are usually fixed, like say, okay, use spheres, box, and cylinders, cones. Those are common ones. But in some applications, you can also people can extend it to like super quadrics or some more complicated situation. So in our experiments, we just choose 4. But of course, I mean theoretically, you can include more things. But it's difficult to automatically introduce that. Or now, when we train this CSG stamp network, so then you have to fix that. Because otherwise, currently the network is not so smart to introduce the new primitive object. Because otherwise, it's difficult to know, okay, which one should be treated as a primitive object, right? Mm-hmm.
Okay, so I think this question is somehow like a dictionary learning. We can say that the basic elements are the dictionary, right? And we in this work we adopt this CSG to like a union or some other strategy to compose them. But in the dictionary learning framework, if the basic elements can be optimized. So, for example, if some indoor scenes, there are some object, the shape is quite is not regular. So if we use this sphere or something like this, maybe it's not the best, right?
Yeah, I think that's possible. So actually, the second work actually is kind of like in this direction. So we replace the primitive object. But now, say, although we don't call them the primitive object, but we call them so extruded parts. But in principle, extruded parts actually serve as a primitive object, right? And on the other hand, sometimes say, you can also use, as you mentioned, say, deep learning. So you have some pre-processes, do some initial analysis from the input data and come up with some relatively complicated shape as a primitive, as some work like say presented by people from this Saint-Flazy University. So they use some like the convex combination of the half plane to form the primitive objects. So then, yeah, so that case, so you can use some way to learn some primitive shapes first, or basic shape first. Then you can plug in this into our this CSG stamp net to do that. That's also possible. But I don't know whether that's a good idea or not. Really, it's a trade-off, right? But just as I said, in the traditional CAD industry, usually the primitives are just those are relatively simple, like sphere, cylinder, cone, box. Those are sufficient for general situation.
Okay. So the second question is a general question. So how do you think the linear network-based method and the linear representation will help the CAD and CAE related problems? So traditional CAD and CAE is like supply or something like this, and proposing a detailed lot of quality work in this field. And recently, this linear-based method or linear representation, like a linear implicit function, and also the CSG stamp network is a new way to for geometry modeling, right? So do you have any suggestions on this research direction?
Well, actually, I have no clear answer to this question, but my thinking like this one, say, okay, so those linear representations, right, actually are quite interesting, especially of interest in the community of computer vision, right? But when you come to like the CAD industry, in those industry which require very high precision representations, so far maybe still there's some problems. But say for the very complicated shapes or things, we want to come up with some more abstract or compact representation. But relatively, the precision might not be so important. Then this linear representation might be quite interesting and useful.
Yes. Okay.
And it also provides some high level, I mean, meaning like semantics there.
Okay. Okay, so there are no more questions. And okay, let's thank Professor Zhen's wonderful talk. Okay.
Okay, thank you. Yeah.
Okay, so next we go to the second part. Maybe okay, Yi can share your screen.
Yes.
Okay. So first, let me introduce Yi. Yi is an assistant professor in Zhejiang University. Prior to that, she worked as a postdoc in MPI for intelligence system and the University of Tübingen. She received her PhD degree from Zhejiang University and bachelor degree from Xi'an University. Her research interest lies in 3D computer vision, including 3D understanding, reconstruction, and controllable image synthesis. Today, she will talk about linear rendering for lower value appearance, semantic, and content synthesis. Okay, let's welcome.
Thank you for your introduction. It's a great honor to be here to share our work on neural rendering for low view appearance, semantic, and content synthesis. And some of the work that I introduced today were done while I was a postdoc in Max Planck Institute and University of Tübingen. So why are we interested in neural rendering? Let's first take a look at the classical rendering pipeline. Here is one example of the classical used in simulation.
Sorry, the voice is not clear, and I cannot hear your voice.
Oh, sorry.
Okay, it's okay now. Yeah, go ahead.
Okay. Should I start again or?
Yeah. I think you can start from the first slide.
Okay. Yeah. Okay. Yeah. It's a great honor to be here to present our work. The appearance, semantic, and content synthesis. I'm Yi from Zhejiang University, and some of the work that I will introduce today were done while I was a postdoc at the MPI, IS, and University of Tübingen. So why are we're interested in neural rendering? Let's first take a look at the classical rendering pipeline. Here is an example of the classical rendering used as a simulator for autonomous driving, named Kala. This simulator, as we can see, it can render per pixel semantic and instance labels. And the photorealism of the rendered images also look good. However, we can still identify that there is a domain gap to the real world. And similarly, if we show such human-created 3D assets to human in the VR or AR devices, we can also immediately recognize that these are not exactly as the same as the real world. And another problem with the manually created 3D assets is that it's actually extremely expensive and time-consuming for the professional artists to create those 3D assets. Here we show one example of a professional artist creating a car in Blender. That's all the, like as a short summary, we can say that if we have manually designed 3D assets, of course, they are very 3D controllable, that where we can manipulate objects, also change the camera viewpoints during rendering. And they can also provide perfect 3D label, provide perfect semantic and instance label in the simulator. However, we can see that there is clearly a domain gap to the real world, and it's also quite expensive to create those 3D assets. So the goal of our talk, of our work in this talk is to create such 3D visual assets from the real world, such that there is no domain gap and it requires no design effort. However, there are, of course, many challenges. For example, it's quite hard to reconstruct such 3D objects from the real world, just as we have seen from the previous talk. And again, it's also not clear how can we integrate semantic information from the real world reconstruction. And furthermore, it's also unclear how can we create unseen content from the real world images. And in this talk, I will talk about the three parts. And the first part will be about novel view appearance synthesis, where the goal is to perform novel view synthesis of a single scene. And beyond that, we would like to incorporate semantic information into the scene such that it can mimic the simulator and it can provide dense semantic information. And while this first two works focus on reconstructing a single scene, we also talk about how can we efficiently create 3D novel assets by learning from data in the third part. Okay, so now let's begin with the first part. How can we achieve novel view appearance synthesis of real-world scenes? I guess we all know that Nerve is now very powerful on this task. It can achieve high fidelity novel view appearance synthesis and also in real world scenarios. And on the left, we show some input images of Nerve, and on the right, it can render quite photorealistic views at arbitrary viewpoints. And just as a quick recall of Nerve, it is basically contains two key components. The first part is how the scene is represented. It's represented as a radiance fields that maps a spatial location X and viewing direction D to an output color and density. The color is dependent on the viewing direction such that it can model non-inversion surface. So this is quite a compact representation as all the information are kept in the ReadyMLP, and it can map any continuous input location to an output color and density. And the second key component of NERF is volume rendering, where for each ray, it samples several points along the ray and accumulate the color along the ray. So while volume rendering, NERF we can obtain the color at every pixel. And during the training process, NERF minimized the per pixel reconstruction loss. And this is all performed in an end-to-end fashion. And also one advantage of NERF is that it has no need to recover perfect geometry as long as it can fit the reconstruction loss and the training views. Here is some results of NERF, and as we can see that NERF can perform quite well on these things, and it is quite photorealistic. So it really brings us the hope that maybe such neural rendering methods can be integrated or even replace the classical rendering pipeline to provide more photorealistic experience. But for novel businesses, there is still, of course, there are still a lot of challenges to really make this practical to real world like AR or VR devices. So one key challenge here is how can we speed up novel view appearance synthesis? Here we present our work, KiloNerf, and for speeding up neural radiance fields. So NERF, why is it slow? NERF is slow because it requires millions queries of deep MLP to render a single image. As we show here, NERF uses a large MLP to represent a single thing, and which means for render a single image, we need to query all the pixels, and for all the pixels, we also need to sample many points along the ray. This leads to millions of queries of a large MLP. So a naive idea is that we can replace the large MLP with a small one. However, this will limit the capacity of the network and the thing will not be represented in the same fidelity. So our key idea is to decompose the thing into many non-overlapping regions uniformly, and we represent each single region using a tiny MLP. This effectively reduces the flops. When combined with empty space skipping and early rate termination, which are classical acceleration methods, we achieve real-time rendering while maintaining the same image quality. Here is a demo we show for KiloNerf, where we can render the in real time on an affordable consumer GPU GTX 1080. So for KiloNerf, some more details about KiloNerf. Here we show the network architecture comparison of NERF and KiloNerf. We show that KiloNerf is much smaller compared to NERF and also has much smaller K-flops. For training, we adopt a two-stage training strategy. In the first stage, we supervise KiloNerf by a trained NERF model. And in the second stage, we fine-tune all tiny MLPs to minimize the image reconstruction loss. We compare, here is a quantitative comparison to the baselines. We show that KiloNerf is significantly faster than NSVF, which is another baseline which also uses early rate termination and empty space skipping. Compared to NERF, the visual fidelity is preserved and sometimes even improved. Another thing worth to mention is the memory cost of KiloNerf is much smaller compared to tabulation-based methods. So actually at the same conference, ICCV 2021, there are some other acceleration methods for NERF that are proposed using tabulation-based, using tabulation. The key idea is to save the intermediate results of the MLP such that we can directly get the intermediate results while looking at the table. And this requires large memory consumption. And in contrast, KiloNerf requires only 100 megabytes GPU memory. Here are some qualitative comparison. We show that KiloNerf can achieve real-time rendering while maintain the same or even better quality. And here is one interesting application that we show both the empty space skipping and early termination, as well as the tiny MLPs. They both contribute to the speed up. And with this combination, we can achieve real-time rendering. And another ablation study here, we show that if we reduce the grid resolution or the network size, both leads to worse performance. And also fine-tuning is necessary for high visual quality. Here we show the image patch without fine-tuning, and we can see these artifacts between the two individual MLPs. And with fine-tuning, these artifacts is gone. Okay, so that's about accelerating novel view appearance synthesis. And thinking about the simulator that I just shown in the beginning, another question we want to address is how to render semantic label at novel viewpoints. This is very helpful towards building a simulator from the real world images. And if we are able to build a simulator from real world images, this can eliminate the domain gap between the simulator and the real world, which hopefully leads to better performance if we train our agent in such a real photorealistic simulator. And as we have seen in the beginning, simulators like color, they should provide full semantic information, which means we would like to render semantic labels at novel viewpoints. And how can we achieve this? So we propose a panoptic nerve for this goal. And the idea here is also quite straightforward. We want to infer semantic and instance label in the 3D space, such that we can obtain 2D panoptic labels while volume rendering. And the input here we consider are sparse images, coarse 3D bounding primitives, and noisy 2D semantic labels that are obtained from a pre-trained 2D neural network. So we apply the pre-trained 2D neural network to the sparse images to obtain these noisy 2D predictions, which are quite easy to obtain. But this is actually not an easy task. Here we show why. So as we have mentioned in the beginning, NERF does not necessarily recover good geometry, especially giving sparse view images. We observe that in the street scene that we consider with such sparse images, NERF fails to recover good geometry. Here is the depth map we render if we run the naive NERF on our sparse view images. And we can see that the geometry is quite bad. So in this case, if we directly assign semantic labels based on the corresponding primitives, then the rendered semantic labels will not be accurate. For example, this part is wrong because the underlying geometry is incorrect. And another challenge is that if we directly assign semantic labels based on 3D bounding primitives, there are ambiguous regions at the overlapping region of the bounding primitives. For example, the car here has intersection with the road, and for the 3D points in this intersection region, then it's very hard to design a correct label. So semantic nerve, a previous work, semantic nerve, it proposed to fuse 2D predictions using nerve, also by inferring semantic labels in the 3D space. However, we observed that denoising is hard, giving bad geometry, because the network can even learn very poor geometry to satisfy the noisy predictions from different viewpoints. And what's also hard is that if the 2D predictions are obtained from the real pre-trained models instead of like Gaussian noise that we add, then in this case, we do not have any assumption on the distribution of the noise, such that it also makes the fusion problem harder. And there is a previous work that we did in our TPMI that we use conditional radiance fields, CRF, to merge the coarse 3D bounding primitives and the noise 2D predictions. What we used there is based on a joint inference over 3D points and the image pixels. So we rely on LiDAR predictions in that work, and we then also rely on accurate 3D reconstruction to determine the visible 3D points on each image. And in this sparse view setting, it's also very difficult to recover such an accurate reconstruction. And in this case, the inaccurate reconstruction also leads to poor performance. So with our panoptic nerve, we improve geometry guided by semantic information. Here is the depth map of our panoptic nerve as compared to the previous nerve geometry. It's much better, and it resolves label ambiguity by unifying 3D and 2D semantic information. Here is the projected semantic label as well as instance label. So how is this done? Here is the method. So we basically have the naive nerve in our pipeline, that is the radiance field. So it also maps the 3D point location and viewing direction to the color and density. But what's more importantly, and the key of our method is this dual semantic formation, where we have one fixed semantic field that is determined by the input bounding primitives. And then we also have a learned semantic field that predict a learnable semantic label at every 3D point. With two fixed semantic field, we can render two semantic maps. And also with the bounding primitives, it provides information of the instance. And we can easily render an instance map. And by combining the instance map and the semantic information, we can obtain the panoptic label. So you may wonder why we want to have these two semantic fields. And that's the kind of the key of our method. So why do we want to have this fixed semantic field? We observe that if we have this fixed semantic field, then we can use semantic information to guide the geometry optimization. So once we run for this branch, we render a semantic map, and we use the noisy 2D prediction as pseudo-ground truth to supervise this semantic label. And as we can see, this can only backpropagate gradients to the density as the semantic part is fixed. So which means if we have a correct 2D pseudo-ground truth, then the underlying geometry can be corrected. And if the pseudo-ground truth is incorrect, but if it does not pass through any bounding primitives along the ray, then the underlying density is not affected. So, and then we also have two other semantic losses defined on this rendered semantic label and the semantic label of the 3D space for this learned semantic field. So here, the main purpose is to address the ambiguity at the intersection region of the bounding primitives. So for this 3D semantic loss, it is only defined, the ground truth is obtained from the fixed semantic field, only if a point is uniquely enclosed by one bounding primitive. And then at the intersection region, the semantic labels are corrected by the pseudo ground truth provided by the noisy 2D predictions. And by merging these two information in the learned semantic field, we're able to resolve the label ambiguity. And as this learned semantic field also shares the improved geometry, that's why the underlying geometry is improved, and then also the semantic label ambiguity is resolved. So here we show comparison to the baselines. On the left, top left, we show the input image, and on here we show the noisy 2D prediction. And for example, our method is able to correct the incorrect region of the noisy 2D prediction. And comparing to the baseline like semantic nerve and our CRF baseline, our method also achieves better performance. And here we show results of panoptic label transfer, where we render panoptic labels. One clear disadvantage of this CRF baseline is that it infers in the 2D image space, which means it suffers from overexposure, as this region is the color are almost the same, and it's really hard for the CRF baseline to distinguish these two instances. In contrast, panoptic nerve is able to distinguish these two buildings because it learns the correct geometry. And what's more importantly, panoptic nerve also enables novel view appearance and synthesis and semantic synthesis as what we want to have in the simulator. Here is a demo that we show panoptic nerve rendering at novel viewpoints with semantic and instance labels. And we also believe that this novel view appearance and semantic benchmark is very important towards building full autonomy system. And so in our KD360 dataset, we released such a benchmark at the intersection of computer vision and graphics. And we also evaluated several state-of-the-art baselines, including NERV and MIP-NERV and PBNR. And we show that there is still some effort to be done to really push this to very good stage. And we are also glad that we have received several submissions to this benchmark. And we also encourage you to try our benchmark and also submit to our benchmark. Okay, now let's move to the last part. The previous two works, they focus on reconstructing or representing a single thing. But how can we learn to generate novel 3D visual contents? Intuitively, when we talk about generating visual contents, we will think about generative models. And generative adversarial network is one of the representative work. For example, this is a result of StyleGAN2, which is able to generate high fidelity and novel contents. And however, StyleGAN2 has no 3D controllability, which means we are not able to control over the camera poses, which means then these images, they are not really useful for gaming or simulation applications. So the intuitive idea is to lift the 2D generator into the 3D space and incorporate the neural rendering into the generator. This leads to our work graph, generative radiance fields, where we want to model generative model for radiance fields. And here it gives an illustration of our generator. We sample from a noise and we also sample input location and viewing direction. And then we represent the scene as a radiance fields. And we use volume rendering to render an image. Note that the discriminator is exactly the same as the original GAN. And it's just the 2D discriminator and unpost to the image collections. Here's a more detailed architecture of our graph. Here is a more detailed architecture of our graph. We show that, so firstly, the radiance fields is not representing a single thing anymore. It's a conditional radiance fields with these two conditions. By drawing two different conditions, it represents different objects. And it's supervised by the adversarial loss instead of per pixel reconstruction loss. During training, we sample camera poses and image patches of size 32 by 32. And here is quite different to the original NeRF, as we don't have the per pixel supervision anymore. And one naive solution is that we first render the full image and have the discriminator defined on discriminative loss defined on the full image. However, as we have already discussed before, it's quite slow to render the full image, and which also leads to slow training and large memory consumption. That's why we fixed the input resolution to the discriminator as 32 by 32, and we randomly sample at different image locations with different scales, such that it can have the discriminator can see both the global and local architecture of the image. And similarly, we also sample such patches from the real images to fit into the discriminator. In this way, we can train at different resolutions. We can train on different resolutions while keeping the memory consumption constant. More detail about the generator is that we inject noise at two different locations. One is together with the input location, and the other is together with the viewing direction. And in this way, we observe that the network automatically disentangle these two and use DS to represent the shape and ZA to represent the appearance. Here is a result of here is a qualitative result of graph, and we show that we can interpolate for the shape and the appearance. And we also conducted some other experiments on cats, birds, and human faces. And of course, this is earlier work, and the image fidelity of the faces are not as high as other follow-ups. So we also were thinking, like, what is limiting the performance of graph? And we observed that actually the patch discriminator is not is kind of an obstacle for really making it high fidelity. So let's take one step back and think about this problem again. In graph, we directly render at the however, it's slow. It has slow rendering, which means it's also very slow for training and also has large memory consumption. There are some other follow-up works that render at low resolution and use a 2D upsampling network, which we call neural rendering, to upscale the image to high resolution. This has fast rendering and also has high image fidelity. However, it may not be mathematically consistent anymore because the neural rendering may not follow the 3D consistency. So we want to ask how to scale to high resolution while keeping multi-view consistency. This leads to our follow-up work, Voxgraph. Inspired by DVGO and Planoxo, which are methods for accelerating training of NeRF, we represent the scene as sparse voxel grids instead of the radio MLP. And the rendering of the sparse voxel grids are very fast. And we also don't need 2D upsampling network. Here is a closer look at the method of our3D convolutional neural network instead of the radio NLP. We generate the 3D voxel grids using such 3D convolutional neural networks, which means we can generate the 3D content in one single forward pass instead of millions of queries of this large NLP. And we also regularize the sparsity of the voxel grids such that it can achieve faster rendering. And what's more, one more detail is that we disentangle the foreground and background to further enhance the sparsity of the foreground object. And during training of Voxgraph, we use pruning and progressive growing. During pruning, we improve the occluded voxels as well as the low density voxels. And during training, we start from the low resolution and progressively grow both the voxel resolution as well as the image resolution. Here is a result of Vox graph. We first compare to some baselines, including StyleNerve. As we can see that StyleNerve uses a powerful neural renderer, which means it may not be consistent, especially at when the viewing angle changes largely. We also compare to GRAM. Similar to us, GRAM does not use a 2D upsampling network. That's why it's much more 3D consistent. However, GRAM's underlying formulation, this manifold formulation, leads to artifacts. And instead, in Vox graph, does not require a neural renderer or a manifold representation, and we can obtain quite consistent performance. Here we show some more results. We show the interpolation in the latent space. And as our method is able to disentangle the foreground and background, we also show results of background removal. As we can see that the method actually can automatically disentangle the foreground and background without any explicit supervision. And we also illustrate the sparse voxel grids. We also show results on cats, as well as its underlying geometry. And yeah, so what's more beyond synthesis? Actually, there is quite straightforward follow-up work of following this generative 3D aware generative model, which we did at ECCV 2022. So the idea is that if we have a generative model, we can perform analysis by synthesis by fixing the parameters of the generative model and using GAN inversion to find the camera pose as well as the latent code. This actually leads to category level 6DOF pose estimation. And we point out that we figure out one issue of this pipeline, that if we directly use gradient descent for GAN inversion, it easily gets stuck in local minimum, especially for the camera pose. And in this work, we explore how to use the generative model as a simulator to train an agent in this environment using imitation learning or reinforcement learning to reach the goal. And yeah, this is a side extension of this work. And if you're interested in this work, you can check our paper for more details. Well, as a short summary, I introduced killer nerve for accelerating novel view appearance synthesis, panoptic nerve for novel view appearance and semantic synthesis, and two 3D aware generative models for creating unseen content. And a few take-home messages. So firstly, neural rendering allows for learning high-fidelity 3D visual assets from 2D images, which is quite powerful. And one more thing is that neural rendering can actually be a general tool for versatile applications, including like simulation or like AR/VR applications. And of course, there are still quite some challenges. For example, we'd like to have more efficient and lightweight representations, representations that are more controllable, like what is shown in the previous talk, that we are able to manipulate them more like user-friendly, and also like scaling to large-scale things is also very important. And lastly, I'd like to thank all my collaborators. And that's all. Thank you.
Thank you. Okay. So very wonderful talk. There are several questions. Okay, the first question is that I can say that the last part is generally is based on this. So it's the generated part is there is a generator and discriminator. It's some like based on this GAN framework. So recently, this the diffusion model is very popular, right? So how do you think? Is there, I mean, is there any possibility to combine this diffusion model with linear radius field?
Yes, very good question. I also thought about this. Yeah, I think I think it's very like interesting direction to think about, but also like to me, it's not like super straightforward, because for images, for diffusion model on the images, we can simply add noise to the images. But for radiance fields, like we don't have 3D supervision, which means it's not straightforward to directly add noise to the 3D space, right? And what we can still do maybe is to add noise to the image space. But this means we need to have we need to model the noise, we need to model the process in the 3D space to invert the noise adding process in the 2D image space. So I think that's like maybe like why there is still not work coming out yet. Like I think that's not like super straightforward. And I know actually one work in has tried something similar, but what they tried is to it's called Gaudi from Apple, and what they tried is to represent, like first learn different things, and then they extract the latent code, and then they just apply this diffusion mode to the latent code. So it's not directly applied to the 3D space or the image space.
Okay, thank you. Okay, so another question that I mean, in the first talk, we can see that Professor discuss or write work about CD field, and we can see that in this is traditional geometry modeling field, the ADAPL. I mean, if we have this geometry model, and there are many users need to edit the models, and one question. For the North-based model is how can we edit the generated model? So how do we have any comments on this question? I mean, there are a lot of people have concerns to this North-based models.
Yeah, that's also a very good question, I think. So I think there are like it depends on like what kind of model that you have. If, for example, if you have like a North model that represents only a single thing, then a natural way, like also there are some works on this, that is to extract a mesh from the nerve model, and then you manipulate the mesh, and then the nerve is deformed correspondingly. And I think that's like kind of one way to do if there is only a nerve representation of a single thing. And what's also interesting is in the generative setting. So if we do have a generative model that can, for example, for the human faces, then the editing can be maybe more high level. For example, there are also some work from Tsinghua University that they try to manipulate the faces based on semantic maps, and this is can be achieved if we in this generative model setting.
Yeah, I think if we based this massive semantic labels, we can do some editing. But another demand is to relighting. So do you have any thoughts how to achieve relighting in this North-based method?
Yeah. For relighting, I think there are also some works in this direction, and I think the most common idea is to really also use the classical graphics rendering pipeline because currently NERF only directly represent the thing as the color and density, and some other works represent this, like some other works try to also integrate the BRDF into NERF, and by really reconstructing the surface and learn the BRDF parameters on the surface, then it can enable relighting.
Okay, thank you. Okay, so yeah, there are not any other questions. So Professor, do you have any questions? Are you here?
Yes, no, I don't have a question. Yeah.
Okay.
Yeah.
Okay. If not, okay, let's finish our today's talk. So let's thank Professor Zhang and Professor Liao's wonderful talk and all the comments and discussions and questions. Okay, so let's finish the talk and see you again. Bye bye.
Thank you. Bye.
Thank you.
Okay.
Bye bye.
Thank you. Bye bye.